Hello, everybody. How are you? Welcome to Ask Math Anything. This is the Memorial Day edition because here we are in United States of America, and today happens to be a national holiday. But national holiday does not apply to mathematics because we actually think about mathematical things all day. As some of you know, I've actually been working on lots of different ways to use math to hopefully help our world get into a better position. If you're new to Ask Math Anything, welcome. The way that this live stream works is that I answer questions that come from the crowd, and they can be about just about anything in math. And what I'll try to do is I'll try to choose questions where I can answer them in a way that would make sense to people who are learning algebra or geometry. That doesn't mean that the questions themselves are just normal algebra and geometry questions. In fact, the questions that are asked are usually not what you'd see in class. But that's why I'm running this, because you don't need another class. You already have a math teacher. The goal of running this live stream is to be able to open up the world of mathematics and science in a way that's understandable to just about everyone. If you have been here before, welcome back. It's a real pleasure to have you, and thanks for making the Ask Math Anything part of your daily routine. Let's see, what should we talk about today? I like things says, my math teacher is you. Oh, it's an honor to be your math teacher. I'm happy to be able to do that for you. But I hope that you also have the fortune of having other math teachers in your life. We need as many as we can. Let's talk about some questions here. Interesting. So I'm looking at all of these different things. Somebody says white pixel moved location. Indeed, it did. That's because I think I clicked a different place before starting this stream. What else can we do here? Oh, that's neat. Sophia Tang asks a question. It looks like a number theory question. I'm not sure if I can solve it because number theory questions are quite hard. When I say quite hard, there are many number theory questions that professional mathematicians can't answer. But I'm a little curious what this one's all about. So let's try. So Sophia Tang says, we have an equation, n squared plus 6n equals x squared. And Sophia's asking, find all the solutions if both x and n are integers. Let's just write this thing down. Find all solutions if both n and x. Both n and x are integers. This looks like a very interesting problem, so let's start to think. Now, does anyone see anything useful to do? Whenever I see n squared plus 6n equals x squared, oh, interesting. So Pietro has an idea, which is not what I was thinking about, but that looks interesting. Pietro says there's a difference of squares here. What if we started with that? Well, when Pietro says difference of squares, what the idea is that this is the same equation as n squared minus, let's not do it that way. Let's do it 6n equals x squared minus n squared. And that's a difference of squares, the same equation as 6n equals x plus n times x minus n. So that's one way we could approach it. And if we have this thing here, you could try to then see how you can split the 6 and the n across here. But I see that there's somebody else who also made a suggestion. Oh, someone has asked, is it just you or is the pen thinner? No, the pen is actually the same width as before. I'm not sure why. I think maybe YouTube's algorithm that they're using today to send the video to you might just be making the video process slightly differently. But so I see another idea. By the way, I see some people are suggesting numbers already that work. That is one thing you could do. You could go and find some n's and some x's that work. Maybe we'll use those later. And I see people are saying that n equals 2 and n equals 4 also work. Okay? So we've got a bunch of n's that work. But I'm going to try to do some algebra first. And I like the idea. I've seen a couple of times. And Adit has also put it up. Adit Ambedkar has also put this up, which is that, look, it looks like n squared plus 6n can be factorized also. So there's another way to say equivalent equation is n times n plus 6 is a perfect square. I actually want to start with this method because I want to go and play a little bit with this. If I want to make a perfect square out of n times n plus 6, how do you make a perfect square? the way you make a perfect square is that you have to have a perfect square times a perfect square, right? Is that true? Is the only way to make a perfect square by multiplying together two perfect squares? Is that the only way? Nope. There's another way. Another way is if they kind of share a common factor, all right? So let's look at this in detail. So if I look at this thing, I have one option. Let's make a few cases. So there's case 1. Some solutions come from case 1 is where n and n plus 6 are both perfect squares. The reason I'm happy with that case, oh wait, you're right. The pen is smaller. Just a second. Now I'm curious what happened. So just a second. You guys were absolutely right. Something got changed. And I'll tell you what happened. What got changed is that I was doing some interview online. And while I was doing that interview, I changed the scales of all of my things. See, I can start moving this all around. Let's see. So let's put that there. And I want to rescale this to the whole... Whoa, how'd that happen? There we go. Let's snap that to the screen. Here we go. You were absolutely right. I didn't realize that something had changed. In that case, what's the other thing that changed? Oh, wow. And my background also changed. Just a second. We're going to fix this. You guys are so perceptive. This shows that some people have definitely been to this live stream before. There you are. Right. So the reason that this changed is because I was actually using the entire studio setup to do TV interviews with TV stations. And that way it was easier I had to scale myself up to be bigger. Okay, let's see. Let's keep going. So case 1 is when I have a perfect square and another perfect square. Now, if that is one of those cases, the reason I'm not so scared of this is that it's not very common that there are two perfect squares that are only 6 apart. Maybe you've noticed, but perfect squares tend to get farther apart. Okay, let's do another case. What's another case? Well, the only other case, case 2, is that they have a common factor, okay? They need to have some common factor, and then after we take that common factor into account, what's left over is a perfect square. We often call that common factor G for the GCD. Case 2 is that n and n plus 6 have GCD, greatest common divisor, equal to some G. In some countries, people call this HCF, highest common factor, and then you'd call it H. But in America, we call it G for GCD. So they have GCD equals to G, and the way it works is that n is equal to G times something, G times, let's call it A, and n plus 6 is G times something, the something is called B, and what's important is that both A and B are perfect squares. And both A and B are perfect squares. Does everyone agree with me that it has to be case 1 or case 2? This is the key to the problem. I think we can solve it now. You see, the key is that either they're already perfect squares or they have some common factor, but after you take that common factor away, then what's left over is a perfect square and a perfect square. Because you see, if you multiply these together, then you get GA times GB, which is G squared, that's how you got this perfect square, times A times B. This is the fundamental insight on this problem. All right? So after you have factorized out all of these common factors, you collect the common ones into G, and you've got perfect square, perfect square. There is no other possibility. Oh, there are 2 overlapping logos. You are right. Now I understand why that background was bigger. That's really interesting. Thanks for being so observant. How's this? Now when I said how's this, I have to actually press this button. There we go. How's this? Much better. Okay. You guys are so observant. This is what happens when you teach a math class to people who are mathematical. I've actually often found out that people who are mathematical think a lot about all these little details. And so if you want to know what I just did is I took the background and I just simply scaled it a little bit bigger so that the logo that was over here has gone out of the screen, because the image we had before happened to have a logo already on it, so we had to scale that out. All right, good. So now let's go back to this. These 2 are the cases. Hey, how many options are for case 1? How can you find 2 perfect squares that differ by exactly 6? Does this ever happen? Are you ever going to have two perfect squares that differ by exactly 6? No, because the perfect squares get farther and farther apart, right? So if I look at the perfect squares here, 1, 4, 9, 16, 25. The differences between these perfect squares are 3, 5, 7, 9, and it just goes up from there. And there's just no way. Okay, so Temp ID said they always have an odd difference. That's true. But if I want to have a difference of 6, I could do it by having like two perfect squares. Perfect squares like one apart, right? Like with another in between. But even if I did that, the smallest I could get is from 1 to 9, which has a difference of 8. So it skips 6. How inconvenient. Absolutely right. So this case 1 actually has no options. So now let's go to case 2. In case 2, I'm saying that they have some GCD. Now this makes us think about something. What possible greatest common divisors could there be between n and n plus 6? This is a neat fact. What numbers could be the GCD of n and n plus 6? I know that not everyone here has taken the number theory class that we teach in our online courses, but I'll just we can see this by example. Let's do a bunch of them and just see an example. There's a neat pattern that comes. Suppose we have n. How should I write this? Yeah, let's write n plus 6, and the GCD of n and n plus 6, okay? Let's choose some numbers, like 1 and 7. What's the GCD of 1 and 7? It's 1. 2 and 8. The GCD of 2 and 8 is 2. 3 and 9. The GCD of 3 and 9 is 3. Clearly, the GCD is the same as the first number, right? Not really. Let's keep going. 4 and 10. The greatest common factor of 4 and 10 is not 4. It's 2. 5 and 11. Ooh, those are relatively prime, meaning that there's no number which divides both of them bigger than 1. Okay? 6 and 12. There's a 6. 7 and 13. Yikes. Those are both prime. 8, 14. 2. Let's keep going. 9 and 15. Greatest common factor of 9 and 15 is 3. 10 and 16, 2. 11 and 17 is 1. And 12, oops, that's not the color I wanted. 12 and 18 is 6. I wrote all of this on purpose. Aha! I like things has said something that I like. I like things, and Pietro both have said there's a pattern. What's the pattern? 1, 2, 3, 2, 1, 6. Wait, I can't read. 1, 2, 3, 2, 1, 6. 1, 2, 3, 2, 1, 6. Oh, there's a pattern. You know why there's a pattern? There's a pattern because it turns out that actually, if you look at these two numbers, every 6, okay, let me put it this way. It turns out that everything that divides both of these also has to divide their difference. There's something going on here, and why I knew there would be a 6 is because there's something called the Euclidean algorithm. The Euclidean algorithm is where you say that the GCD of two numbers is the same as the GCD of one number and their difference. So there's an important thing here, which I saw when the question was asked. This is the same as the GCD of n and 6. You see, there's a reason why. It's because this 6 here, oh, the last row has cut off its half. You're right. I'm sorry. It's because, all right, now you guys are very curious how my technology is working, it seems. So the way that I can explain to you what's going on there, let's go to this. So let's give it some more. Now I have to see. Cancel this. Oop, get out of here. Filters. Yes. Crop. So what we're going to do is we're going to give it some more space. Well, actually, you know what? I'm not going to go and mess with that right now. So let's just continue this as we go. There's a crop at the bottom. The reason why there's a crop at the bottom, oh, you know what? Okay, I will let you know, because you guys are also interested in all these things. Here's what's actually going on. Close. So now you can actually see what my real screen is. The reason there's a crop at the bottom is because what I was actually doing, oh, can you see that? Or did it freeze? So, okay, the reason there's a crop at the bottom is because that's actually where I choose my colors. So what's going on this screen is I actually just cropped off the line where I choose my colors. And now what you can see is that whenever I tap down there, that's how I get these colors. Everyone was always wondering, how can you make this thing where you have all these different colors appearing? It's because I just hid the palette for you. But it's okay. So we just showed it here. You guys are finding out more about my studio every day. But now let's keep going. So I have the GCD of n and 6. And the reason is because any number which divides two numbers also divides their difference, right? Like the Euclidean algorithm, thanks for asking Batmobile. The Euclidean algorithm is saying, look, if I want to know a number that divides two numbers, it also divides their difference, right? Like if I have a number that divides both 6, if 6 is a multiple of it and 9 is a multiple of it, then 9 minus 6, which is 3, is also a multiple of it. So that's what I've done here. I just said that the GCD of n and n plus 6 is the same as the GCD of the first one and the difference between the two. So this is kind of nifty. Now, once you know this, that actually tells you that the GCD is going to repeat every 6 because the GCD of the answer is the same as the GCD of n and 6, which of course repeats every 6 that you have n. Okay, but the reason I did this is because now I can split into cases based on what the GCD is. Remember that case 2. Case 2 here was to say that n and n plus 6 have a GCD. And here I mean the GCD is not 1. If the GCD is 1, we're up in that case. So now let's just look at the GCDs. We have 2, 3, and 6 as the possibilities, right? So let's finish. Case 2a, which is that the GCD of n and n plus 6 is equal to 2. In that case, what I need is I need to have that this is 2 times a perfect square. I'm going to write a square. That's supposed to be 2 times a square, okay? And then this is also supposed to be 2 times another square. I'll use a different color. So I need to have 2 times a square and 2 times another square, and they need to be different by 6, right? So I need to have the green square and the blue square differ by 3. Is that possible? Is it possible to have that blue square equals green square plus 3? Does anyone know any perfect squares where the blue square is 3 more than the green square? Yes, temp ID, 1 and 4. So what I could do is I could say that this happens to be 2 times 4, and this happens to be 2 times 1. In that case, I have one answer for n already. One answer for n is 2 times 1, or 2, right? One of the possibilities for n is n equals 2, n plus 6 is equal to 8. And this works. 2 times 8 is indeed 16. That's a perfect square. Okay, so we got one of the cases already. One of the answers. This thing gave that one answer is n is equal to 2, and the x is equal to the square root of 2 times 8, that's 4. And this was one of the answers that people had suggested in the chat. Well, what else can we have? Case 2b. Let's use a different color. Case 2b. The GCD of n and n plus 6 is equal to 3. Could that be done? Well, then I need to have 3 times the square, and the other one has to be 3 times another square. Does anyone know a way I could have these two squares differing by 2? Do you see what I mean? Over here in the second case 2a, we had the two squares differ by 3 because it was 2 times the square and 2 times the square, and they differed by 6. Here I need to have 3 times the square, 3 times the square differ by 6. So the two squares have to differ by 2. It's not possible. There's no way to do this. This has to differ by 2. and that's impossible. Okay? Let's finish. Case 2c. The GCD of n and n plus 6 needs to be 6. How do I do this? If I want that to happen, well, we know the trick now. It's just that each of them has to be 6 times the square. So over here, I have 6 times the square. And over here, I have 6 times another square. So I need now that these two squares differ by 1. Does anyone know any two squares that differ by 1? Oh, just a second. So we have a question. So Mukta Ramesh asks, why won't 0 and 3 work for case 2b? Well, let's see. Oh, the reason why 0 and 3 won't work is because I need that 3 times this square is n, and 3 times this square is n plus 6. So what I need is that 3 times the squares differ by 6. That means I need that the squares differ by 2, right? The point is that I need that the squares themselves differ by 2 so that I can have that 3 times the squares differs by 6. But there are no two squares that differ by just 2. Okay? 1 and 3 aren't squares. That's why, Brian Lee, thanks for asking. 1 and 3 differ by 2. But unfortunately, 1 and 3 aren't squares. It's essential that we have 3 times a square and 3 times a square. That was why we used these cases. The case 2 was there's a greatest common factor, which comes out. And then after that, I have a perfect square left and I have a perfect square left. So now, let's finish. How can I find two perfect squares that 6 times them differ by 6? Then I need to have two perfect squares that if I take the difference between them, their difference is 1. Oh, I know a way I could find two perfect squares that differ by 1. I could do it with 0 and 1. So I could do it where this one is 0 and this one is 1. And so if this is 0 and this is 1, they differ by 6. And in that case, I have a case where n is equal to 0, n plus 6 is 6, and x squared is supposed to be 0 times 6, so x is 0. And this gives the other solution. N equals 0, x equals 0. And since that was all the cases, I'm done. So this actually finishes the question. It was quite interesting. If you can see the way that we ended up doing this problem, thank you very much for asking the problem. The way we did this is by, messing around with a few things, looking for patterns, and then ultimately realizing that, if you split into these cases in the right way, there isn't actually that much more you have to worry about. Plausible thing asked, what about -1 and 0? -1 and 0 also differ by 1. But there's a problem. You can't have -1 as a perfect square, right? The issue here is that we need to have, there are more solutions. There are negative solutions. Thanks for telling us. So in that case, that means there are more solutions. Just a second. Now we have to look at this. So n and n plus 6, perfect squares. Oh my gosh, thank you. You're right. There are more solutions. So I appreciate the all caps message by Sophia Tang. There are more solutions. And that's because I forgot about the case where the GCD was a negative number. You see, here we wrote the GCDs of 2 and 3, but if you look at how I got the whole thing, over here, why does G have to be positive? G could be a negative number also. And so if I let G be a negative number, I also need to worry about the case where G is like -1 or something, okay? So there's some more cases. G could be -1, G could be -2, -3, and -6. Let's make sure that we have all of those taken care of. Thank you very much. So now, those are all the cases which are the positive ones, where the G happens to be positive things. But what about the case where G is -1? Let's try. So I guess we're on case 2D. That's supposed to be a D. Case 2D, which says that the GCD of n and n plus 6 is equal to -1. Oh, I don't even want to call it that way. It's a funny thing to call that a GCD. So I'm going to put a quotes around the equal sign. The GCD of positive and negative numbers, you always use a positive GCD. But by this -1, what I mean specifically is that what we have here is minus a perfect square. And what we have here is -1 times a perfect square. But just from before, we already know there's no way to make two perfect squares whose difference is 6. Even though there's a minus sign in front, the difference is still 6. Okay, so we don't need to worry about this. So this one has no, it's not possible. No solution, since perfect squares don't differ by 6. Okay? Case 2e. We'll be done soon. Suppose that the GCD equals minus 2. In that case, if it's minus 2, then what I have is I have minus 2 times a perfect square, and the other one is minus 2 times another perfect square. So now what I need is that these two perfect squares have to differ by 6, and the one on the right needs to be 6 bigger. In that case, I need to have two perfect squares that differ by 3. If I want to have two perfect squares that differ by 3, that's 1 and 4. But remember, the one on the right is supposed to be bigger. So that should be 1, and that should be 4. Is this making sense to people? This is the n, and this is the n plus 6. So if this is the n, and this is the n plus 6, the n is minus 8, the n plus 6 is minus 2, that's okay. And if you multiply them together, how to get the x squared? Oh, right. Actually, we also saw some other stuff here. If the x is 4, x could be also minus 4. Because there are two ways to square to 16, so we have to have that too. So this is n equals 2, x equals 4, n equals 2, x equals negative 4. Over here, what are the cases we get? What are the answers we get? Here we get n equals, well, it was minus 8. Minus 2 times 4 is minus 8. And x equals minus 8 times minus 2, take a square root. I'll write plus or minus 4. So that's another solution. X equals minus 8. N equals minus 8. X equals plus or minus 4. And now let's finish them off. The other ones should have no interesting solutions. Case 2f. If the GCD of n and n plus 6 equals minus 3, then over here I have minus 3 times the square. Over there I have minus 2 times the square. No, minus 3 times the square. But there's no squares that differ by 2. So there's nothing here, because that's minus 3 times something differing by 6. So the squares have to differ by 2. There's also no solutions. And the same thing that happened at the end, 2g, if the GCD of n and n plus 6 is equal to minus 6, then what I have is it has to be like negative 6 times something, and the other one has to be negative 6 times something. I can do that. The way I'll do that is I'll take negative 6 times 1 and negative 6 times 0, and what that gives me as a solution is n equals minus 6, because that's minus 6 times 1, so it's minus 6. And if I multiply minus 6 times 1 times minus 6 times 0, that gives me 0, so that's x equals 0. Sophia Tang, is this all of the solutions now? So we now have more of these solutions that we have figured out. Oh wait, did I read that wrong? No, it's okay. Minus 6 and 0, right? Yes! So we got everything right. Thank you very much, Sophia, for asking the question. So this is a pretty interesting problem. This problem is one which at first looks insane, because how would you try to guess all the different values of x and n? But if you use the GCD to go and figure this all out, you only have a certain specific number of cases, which I did really, really slowly just to walk you through the logic. But if you were trying to do this in a hurry, you could actually probably be done very quickly. Okay, so that was a neat question. And thanks again for also pointing out that negative answers are allowed to be part of the answers for this problem. What other questions should we do? Let's see. Oh, wow. So there's a question about how to explain the fourth dimension. And we've seen that question asked for many days in the chat now, so definitely we should try to hit this one. Well, the difficulty about the fourth dimension is it's very hard to draw. In fact, even the third dimension is very hard to draw. When you try to draw a three-dimensional picture, it's not really clear what's going on with the fourth dimension. To me, if I wanted to visualize what the fourth dimension is, it's usually thought of as time. And I might even think of it as like an airplane moving through the air. Because the airplane is a three-dimensional, it's moving in 3D, right? Airplane, not like a car. A car kind of drives on the ground, and you rarely think about the car flying. But if you have something that's flying, the thing that's flying has both some kind of a XY position, which is latitude, longitude position, like where it is on a surface, but it also has an altitude. It has 3 dimensions. And then when you're talking about flying over time, then you're basically seeing that the airplane's position is not the same at every moment. So that's I guess how I would try to visualize the 4th dimension. I almost imagine a movie in my head of something actually happening, moving through time. But it's quite hard to draw. I've never actually successfully drawn a 4-dimensional object. At the same time, usually when I'm thinking about these kinds of problems that have all 4 dimensions, oftentimes one of the best solutions is to try to move into what's called the reference frame of one of the objects that's moving. It's too complicated to have all 4 dimensions moving. So it's a lot easier if you could try to make it so that, if you have multiple things moving around, you pretend that you're riding in one of those airplanes and watching everything else move relative to you. So that's a way of at least making the problem a bit easier to handle. But otherwise, I don't actually have a great way to visualize the 4th dimension. We just try to solve the problems where we think about what it actually means. All right, what do we have here? Oh, interesting. Somebody, AC, has asked, how do you make a password that is super easy to remember, but also foolproof so that no one else can hack into it? I think that clearly the best password in the entire world is just PASSWORD, right? No. That's actually one of the most common passwords in the world. Don't use that. But unfortunately, there are also some other very common passwords. Another very common password, get ready for this, is 1, 2, 3, 4, 5, 6. So somehow these are very, very common passwords. What makes them common? What makes them common is that somehow they have very little chaos in them. They're not very random. They're like the first things that you'd ever think of. Some people are saying, the best password is A. Let me tell you a password that I used to use for my laptop. I don't anymore, so I can tell you what it is. But it was not a very secure laptop. I didn't care too much. The password was \. Just like the \/ key. Like the one letter, the \. And somehow nobody ever thought to guess that. Everyone was always trying to type in all kinds of other nonsense stuff. No, not the /, not the division thing. The \/ is very, very well positioned. It's right next to the enter key. You're absolutely right. So the P14YR0N3, it is because it is right next to the enter key. So the way you would log in is you just go ka-chunk and you'd be in. Now, the \/ actually worked for a long time. Nobody ever guessed that password, but it was in fact very convenient. And I stopped using that when computers got more networked, and then anyone who was guessing could just like connect to my computer and remotely try all the 1-character things and they'd get in right away. So don't use that. Now, if you want to go and make a password that's harder for other people to guess, a technique that I've actually heard many people use is you choose like some song, and then you just go and choose a certain point in the song, and you just put all like the first letter of every word. What I'm trying to say is that you want something that looks completely random to anyone else, but if you yourself think about that song, you're like, oh, yeah, I just go and sing that song and it goes da, 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 like this. What I'm trying to say is that it's back to this notion of what is random and what is not. The more random something is, the harder it is to guess. But the more random something is, the harder it is for you to remember. And so what you want is you want to find some piece of information that for whatever weird reason is stored in your head, but not in anyone else's head. And at that point, it's just like stored in your head for some reason, and you can just use that as your password. Some people also do these things like using certain characters, of course, put a minus sign, put like a plus sign, put a number, replace the O with a 0. You can do all these kinds of things. But I think ultimately what you want is you want to have a password that means something to you, and then it'll be easier for you to remember, but it should mean something only to you. Okay, somebody says just use a password saver. That is good if you trust the password saver. How do you know the person who made the password saver is really saving your password? So I didn't actually ever dare to use a password saver, only for the reason that I didn't know who made the password saver, right? Or you can program your own, says TempID, and that is actually exactly what I did. So I actually wrote my own password saver, and my own password saver uses encryption. It's actually the kind of encryption they use to communicate things on the internet. It's called RSA. So I actually wrote my own password saver where I have my own password to open the password saver, and it's my own program. And at that point, you don't need to worry. Okay, great. Let's go and see. What other... Oh, wow, Paperboy, you're pretty good. Your password is the first 100 digits of pi. I would not be able to get into your account. Although with Wolfram Alpha, maybe I could. Let's keep going. What other questions can we have? I'm trying to see some questions that might give us something interesting that we can talk about. Batmobile has asked, what is 1% of 2% of 3% of 4% of 100% of 10,000? Approximately 0. I mean, it happens to be that you're multiplying together all of these things, and all of the percents are pretty small. And so if you multiply together a lot of very small things, you get very, very close to 0. If you want to know exactly what it is, unfortunately, we don't have a good way of writing down 100 factorial. But that's related to what you have. It's like multiplying numbers 1 times 2 all the way up to 100. More questions. I'm trying to see some questions that might work for answering things for lots of people. Okay. Here's a question that I don't know the answer to, and maybe we won't be able to figure it out, but let's try. It could be hard. Let's buckle up. This is a question by Adit Ambadkar. And what this question says is, create a row of 6 squares. That one I can do. I'll make you a row of 6 squares. Let's pretend these are squares, okay? Create a row of 6 squares. Now, place x, y, and z in the first 3 squares, respectively. Okay. Oh no, the question disappeared. But that's okay. I think I know what the question was. The question was, you want to move the x, y, z all the way to the right. And you can do it by moving each letter 1 square to the right. I think. Oh, here it is. Moving letters 1 space to the right at a time. How many ways do you have to go and push the x, y, z all the way to the right? How many ways can you push the x, y, z all the way to the right? You want to turn it into this. And the question is how to turn from here to here if the only thing you can do is you can move the letter 1 over to the right at a time. Let's think about this. It's a counting problem, right? The question is how many ways can you do this? I'm looking at this and I'm seeing the total number of moves that we have to make. Z has to move a total of 3 times, Y has to move 3 times, and X has to move 3 times. So there's like 3 plus 3 plus 3. There's 9 moves going all together. So that doesn't look good for listing. Is it 27? Well, the tricky thing here is that certain things you can't move right away, right? So there are, by the way, there are only 9 different steps that we're going to take. So the way you can think of it is X is going to move 3 times, Y is going to move 3 times, and Z is going to move 3 times. Let's see if we can think about it in terms of like the order of how we would say what happened, right? I could imagine that we could have some instructions. Here's one instruction for how to do this. This instruction says move Z, and then move Y, and then move X, and then move Z, and then move Z, and then move Y, and then X, and then X. What this instruction means is this is saying which ones are you moving at which times. So Z moves first, and you bump it over. Then Y moves, bump it over. Then X moves, you bump it over. So after this point, after the Z, Y, X, what you have accomplished is that somehow these have shifted 1 to the right. And then it goes Z, Z. So the Z goes tut, tut, and then the Y goes over by 2, and then the X goes over by 2. And that's one of these possibilities. But now, oh, what if you can move backwards? I didn't know that that was an option. If you're allowed to move backwards, the answer is infinity. Because then I can just go and say, hi, I'm Z. I feel like just moving back and forth lots and lots and lots of times, and I'll just do it whatever I want. And then the answer is infinity, and that would be too easy of a problem. So we're going to say that all the things can only move to the right. So here's one way. And this gives us an what we call an upper limit, an upper bound on how many different possible ways there would be, because I can look at how many ways I can rearrange this sequence. This is like if I want to know how many ways could I possibly have a sequence of things with these z's and y's and x's and 9 of these things, there is actually a way to figure out how many ways you can rearrange all of these. But a lot of them are not actually legitimate possibilities. Okay, so I'm looking at this and I'm trying to think, is this the kind of question that we can do quickly here? This looks like it's probably going to be quite complicated. You see, the problem with combinatorics problems is that there's like two different kinds of them. One kind of them is like very nice, there's a simple answer. But then there's also some kinds of them where the solution does involve like working through a lot of cases. And I'm just trying to look through this to see, is there a way that I could reasonably say this one could be done nicely? And I'll tell you, the reason I'm thinking this is complicated is because this is basically a three-dimensional version of what's called the Catalan number problem. Yeah, this is the three-dimensional version of what's called a Catalan number problem, and the Catalan numbers problem is already considered to be quite difficult. So I'm going to say that this one's probably not appropriate for this live stream, but here's what I'm going to tell you. I'm going to tell you what it's related to, okay? Because this is a harder version of a certain problem, for which that other problem we could also, so I bet that what you'd do is you'd go and adapt what we do for the other problem to work on here. And that actually might do the trick. But let me tell you about the other problem. The other problem is a simpler one, but it actually is still hard to figure out. The simpler one, and you don't need to give up. I'm simply saying that somehow for the time period that we have here, the Catalan number problem, which is the one with just x and y, is already quite complicated. But I think I might be able to talk about the x and y one. So let's change this question to make it a little bit easier. Okay. So the one it's related to is to say, let's forget about x, y, and z. Oh, if there's just x, it's too easy. Just make x go across. You are right. You can turn this into a recursion. But it's still like the recursion will be a bit more messy than what I want to do in this particular live stream, right? I basically want to make, I usually want to use this live stream to talk about things that are as understandable to people as possible. So here, I'm going to instead say, what happens if you had just x and y? Okay? If you had just x and y, what does this turn into? It turns into a different problem. You still write instructions, but you know the instructions are y has to go over by 1, 2, 3, 4 spaces, and x has to go over 4 spaces. So you could do like y, y, x, y, x, x, y, x. So what is going on here is that the y's are going across. So I have y's and then x's. So what this is saying is first move the y, boop, it goes over there. Actually, let's actually do this, okay? First is yy. After yy, you're here. That's after the yy. Then the x happens. X moves. X walks one step forward and gets to here, okay? The next thing that happens is that y moves again. This is a really nice problem. So y moves again. And then x says, I'm going to catch up. And the x moves by 2 steps. X, x. Now, the y moves, and it gets away over to here. And then the x moves last. And then we've done it. So do you see how this went? What happened here? So what happened here is that x and y can talk. I guess they can. So x and y are over here, and they also have emotions. Y is trying to run away from x. Okay, anyway, the x and the y are moving across, and this is the set of instructions. And the instructions, this is legitimate. This is an okay set of instructions. Now let me show you a not okay set of instructions. Here is a bad set of instructions. Y, x, x, y. Oh, why not? Y, x, x, y. Because remember, x and y both have to move 4 steps. And this is 4 steps, right? Y happened to move 4 times, x happened to move 4 times. Looks legitimate. But what happens? Well, y moves first. Hooray, y's over here. But look what happens next. X. X will step on y. Oh no. That's not okay. They can't both be on the same square. So that's not okay. All right? So what we're seeing here is with this is bad and that is good. Now I want to show you another way to look at this. I don't want to call them x and y. X and y, those are not very descriptive names. I have a better way. I'm going to call this open parentheses and close parentheses. And I want to make open parentheses get up all the way to the right and close parentheses get up to there. Now, why did I do that? Well, here's a legit set of instructions. What does the legit set of instructions look like? Why? Why change the name? Y is now called open parentheses. Y's name is open parentheses. X's name is close parentheses. Y is open, X is close, X is close, Y is open, X is close. Let's look at the bad set of instructions. The bad set of instructions, remember that Y is open parentheses, right? This is where Y used to be. Y is open parentheses, close parentheses, close parentheses, open parentheses, open parentheses, close parentheses, close parentheses, open parentheses. Now, can someone tell me what is bad about this and good about that? What is bad about the green thing and what is good about the yellow thing? Yes, Grace Yan, you can't close the parentheses before opening one. You see, actually, the entire thing we just did, if it's just x and y going to just x and y, is that you have to have matching parentheses because the x and the y both moved the same number of spots. That's like both of them need to have 4 opens and 4 closes, right? And the yellow one is okay. You never close more than you open. And the green one is bad. You closed before you opened, right? It's like open, close, close. What do you mean close? What if you opened? You can't close. This doesn't work. Lisp programming language. Yes, this is related to programming as well. It just doesn't work. You can't close. So, in fact, the number of ways to do the XY problem is the number of ways to arrange 4 sets of parentheses in a legitimate way. So, the XY problem with 6 squares is exactly the same as the number of ways to make a legit arrangement of 4 pairs. Okay, 4 pairs of parentheses. Now, this is a very famous problem. This is called the Catalan numbers. If you are curious afterwards, you can look this up. This is called the Catalan numbers. And the Catalan numbers are saying how many different ways are there to make some set of parentheses in a legit way. And that's an entire lesson in combinatorics. And that's why, when I saw your problem about x, y, z, and I just started thinking, I was like, I see. You basically have a 3-dimensional version of Catalan numbers. When I say 3-dimensional version, there's a way to find the Catalan number by drawing a 2-dimensional object and doing something called the reflection principle. If you're curious about this, just search on the internet afterwards. But effectively, what you were interested in is a 3-dimensional version where there's 3 symbols, not just open parentheses and close parentheses, and presumably you try to attack it that similar way. So yes, there should be some interesting way to solve your problem, but it's just not quite the right level for this live stream that we're running. But I hope that what I just explained here makes sense to anyone, whether you were taking algebra or geometry or anything. It's just like the math of the XY problem is the same as the math for this thing. And what math is about is trying to connect different looking problems together. Because once you've done that, you can say, yes, everything I knew in the world to solve that other problem, I can now use to solve this one. Okay, what else can we talk about? We got some time still. We've been talking about some deep questions today. We've been sort of grabbing some problems and going quite deep into them. Somebody has changed their name to backslash. Backslash, backslash. What comes after 0? Is it 0.000000000? Well, you see, if you have real numbers, or even if you have rational numbers, there is no number that comes right after 0. And that's one of these amazing things about the number system. There's only a next number if you're doing something with what are called discrete sets. And for example, the integers are 1. After 0 is 1, and after 1 is 2, and so on. People seem to really like this backslash. Please do not use backslash as your password. That no longer works today. That was only a good idea a long time ago, before people could connect to your computer over the internet. Because if people are connecting to your computer over the internet, the way they crack your password is they try all the different one-letter things first. That only worked well in person, where like the way to log in is to go ka-chunk. Okay. Oh yeah, and I did that before they had like fingerprint ID, right? So the whole point was there wasn't a nice easy way to get into something, so my finger ID was just backslash. Oh, interesting question. Oxoboro asked, did you have a personal math teacher when you were younger, or you were studying math on your own? Well, when I was younger, my mother taught me a lot of math when I was in elementary school and middle school. In middle school, it was more like we were working on the hard math contest problems, and I would try them and she would be working on them, and she would explain some of them to me. But eventually after that, when I went to high school, a lot of what I learned ended up being somewhat my own stuff. I would go and do these Math Olympiad problems and these AIME problems, AIME problems, and I would just try to read the solutions and figure it out from there. And effectively, once I started high school, a lot of the things that I learned, I had to go and learn on my own. But I will tell you, that's worth it, right? It's really worth it to try to figure out how you can learn from your own online resources yourself. Oh, of course, you have to use some resources. I just mean there wasn't a teacher. But you go and find your own resources and you learn from whatever you can online. Because these days, the kinds of problems that you're trying to solve, like in the real world, those aren't things usually that people have already solved. Like I can tell you what I've been thinking about for the last 3 days straight. We have this thing inside Novid which senses distance using ultrasound. And what I've been doing is I've been doing a lot of work with, like if you go and measure with a microphone and you record a signal, the sound file you record just looks like some crazy wiggly thing. And it's like, how do you go and make any sense out of the wiggly thing? It's actually quite hard. And so I've been using all kinds of different areas of math and whatever I can learn to try to figure this out. And since I have to do this now, it's been useful that a long time ago, that's also how I learned too. Oh, interesting. Somebody has asked, are fingerprint passwords good? Unfortunately, fingerprints supposedly can also be hacked. Supposedly on your phone, you have left so many fingerprints on your phone that if somebody went to go and figure out, if they got your phone, they could actually figure out your fingerprint. And this is not like brand new discovery. I think like all the movies for decades have always been the criminal left fingerprints. Right? So it's like fingerprints are everywhere, and certainly they're on your phone. I don't know that many people who use their phones wearing gloves. So unfortunately, there are fingerprints everywhere on your phone, and somebody could in theory go and grab that. So that's too bad. You guys have a good sense of hearing. There was a helicopter that went overhead. Somebody else asked, what about Face ID? Face ID is interesting. I think that it's probably harder to crack the Face ID than it is to crack the fingerprint, because the fingerprint you can just grab off the phone. But for the Face ID part, you'd actually need some three-dimensional model which is the same as the face. Although nowadays, because apparently people, Apple rolled out something new so that if you're wearing a mask, you can still get in. I would expect that the Face ID, unfortunately, is a little bit less secure now because somehow half your face is covered. Batmobile asks, how should I prepare for AOIME? So this contest that a lot of people can play with now. I would just recommend you try the old AIME problems and spend a lot of time working with them, and then you'll get better at solving these very hard problems that you otherwise don't know how to start. Actually, don't worry too much about trying just to win the contest. In fact, use all these old problems to teach yourself how to think about something really hard. Sort of like what you just saw us trying to do here with the X, Y, and Z. The way we were doing this is we started playing with it a little bit, we wrote some instructions, and then we started noticing some pattern and remembering some stuff that we had learned before in mathematics. And the only way to learn how to do this is to fight with the questions yourself. I strongly recommend that if you are interested in any of these things, go and make sure you spend enough time working on problems that are actually legitimately challenging for you, but not too hard. And ideally, if you can do it with hints around, that's even better. What else do we have? Ah, I'm trying to see what we should do. So we've done a whole lot of these different, um, yeah, we've done a whole lot of these different specific math problems already, or rather we've done a few in great depth. So maybe I'll go and try to take some things which are a little bit more general here. So that's interesting. Noam Yakar has asked, do you have experience with machine learning calculus? This is pretty interesting. I had seen some articles about how I think Facebook had managed to use machine learning, which is computers, where the computer would itself learn how to solve some problems. It was doing pattern matching, and it was able to do problems on the AP calculus test. When I saw this happen, my immediate conclusion was, aha, that means the AP calculus problems, unfortunately, have become too mechanical. Actually, what the machine learning is good at is it's good at finding patterns. So these computer methods are looking at, here's what the problem looks like, and here's what this answer is. And they would find a pattern. And indeed, as I've shown before, I mean, I bet that we don't need that much mathematical sophistication to figure out these patterns. Hey, I challenge all the elementary school students in the world. See if you can figure out what the pattern is. And the question is, what is d over dt of t to the fifth? I think a lot of people got it. What do you do? Doesn't look like rocket science. Yes, Skylar is right. This is called taking the derivative. But, oh, come on. You just take the number and put it in front, and you go and subtract 1. And this is just one example. Okay, calculus is more sophisticated than this. It has more questions. However, if you think about the machine learning calculus, my opinion is that what's really happening is it's just finding that the problems that are being asked on a calculus test are pretty formulaic, where you could just look at this and you can go and say, oh yeah, whenever I see something like this, I do that. It's a pattern matching thing. And so, yes, this Calculus 101, I do believe that people have already managed to write things where the computer is able to solve these standard, very formulaic problems. But if your question was, does the computer actually legitimately understand calculus? My answer would be almost definitely not. In fact, most people in the world don't understand calculus, in the sense that most people, when they learn calculus, they just do it by following the pattern. But if you want to understand it, you need to understand what this even means in the first place. Like, what's this d over d something? It's actually what's called a limit. And there's a reason why all of these formulas are true. That's actually understanding calculus. I think it's going to be a long way before the computers actually are able to do things with understanding, as opposed to just matching patterns. But then you might ask, isn't it enough just to match patterns? Most of the time. And then you get the next question. Hey, let's figure this out. D over dx, e to the power x. At this point, what do? Oh, maybe I shouldn't have done an e. E looks like a letter, too. Like do something like this. It's like, I mean, come on, what else do? You just take the thing on top and you put it in the front, like x minus 1, and then you take the 2 and it's x minus 1, right? Uh-oh, that's not true. This actually doesn't work. No, this is completely false. Because the problem is that, before anyone copies this down, that is false. So everyone should know that is not how it works. You're not allowed to do that. And that's because this is not following any definitions. And of course, the sharp people who are watching will say, it wasn't exactly the same pattern because the x went up there. Okay? But I'm simply saying that the issue here is if you just do things where you match patterns, at some point you get a thing which is outside the pattern. And unfortunately, when it's outside the pattern and all you've done is memorize the pattern or use a computer to memorize the pattern, it doesn't work. And so that's my main concern with the machine learning solutions. I am actually one of the old school, pure mathematics, applied mathematics, models, first principles, things based in physics. I like to understand that there's a reason why each of these things is being done, and it matches the physics of the physical world. And in that sense, then I say, I believe this model. I'm one of these people for whom it's like, if it's just something where it's like, oh yeah, the machine found that there was a pattern. How do I know the pattern always works? You know, what if it's like this? Okay, well, a car went by, you're right, or a motorcycle, or whatever that thing was. This is what happens when you are working in a place which is surrounded by college students who are having fun. But unfortunately, our fun for today has run into 5 o'clock. So I guess I'll have to say the Ask Math Anything show, unfortunately, is going to end around now. If you liked what you saw, please do join us again. We have actually 222 people watching right now, which is a neat number. But also, if you want to keep in touch, actually, we also have a mailing list if you want to be alerted whenever there are any interesting collaborations coming up. I think that's actually probably somewhere down in the description. I'll see you tomorrow. Tomorrow is 4 o'clock p.m. Eastern Time again, and that's a regular school day, regular work day, and it's going to be a regular Ask Math Anything. See you then.